students, and welcome back to Atomic Bonds. And today will be our conclusion of Atomic Bonds before we get to your lab activity tomorrow. So yesterday, you may recall, we discussed valence electrons a lot. If you don't remember what valence electrons are before you even go on with today's lesson, go back to yesterday and reinforce the whole importance of valence electrons. Super duper important, folks. Super duper important. But for now, let's move on to three bonds. Three bonds. Can any of you name the three bonds? I'll give you a moment. See if you can name the three bonds. I hear some funky names coming out of some of your mouths, but when I think of the three bonds, I think of Bond, James Bond, Sean Connery, Roger Moore, and Daniel Craig. Do any of you have a favorite Bond yourself? The original or the most recent, whose film has been delayed 3 times already, and I'm dying to see it in the big screen in the theater, but they keep on delaying it for some reason. Yeah, you all know why. All right, so, no, these are not the types of bonds we are making reference to here today. We're making reference today to the 3 types of atomic bonds. And the 3 types of atomic bonds are ionic, covalent, and metallic. So today we're going to explore each of these 3 types of bonds: ionic, covalent, and metallic. So let's begin with ionic bonds. Think of the name ionic. Not moronic, ionic. Ionic has an IC at the end of the word, which means it's just turned into an adjective form of the word ion. Think of what an ion is from weeks ago. Do any of you remember what an ion is? It is a charged element. In other words, an element with an unbalanced number of positives and negatives. We can have either a positive ion or a negative ion based upon the relative numbers of protons and electrons. So ionic bonds are going to have something to do with charged atoms, either positive or negative, just based on the name alone. But in addition to that, there's a very important characteristic or component about ionic bonds, and that is this. Ionic bonds involve the transfer, and that word transfer means movement, of valence electrons. Yes, there's that word valence again. You're going to see a lot of it. Ionic bonds involve the transfer of valence electrons. In your notes, you might even want to underline the word transfer, underline ionic, maybe even put a line between the two so that you can study ionic transfer, ionic transfer. Ionic bonds involve a transfer of valence electrons. And as we continue with this type of bond, I hope that you will see why it's called an ionic bond. Now, this whole concept of transfer or movement of valence electrons comes into yesterday's discussion about stability. Do you remember yesterday talking about how atoms achieve stability. How does an atom achieve stability? What has to happen? Its outer energy level needs to be complete. When the outer energy level is complete, then that atom is stable. And remember, in nature, everything seeks a steady state. We all want to achieve a steady state. I'm sure most of you watching this would like nothing more than to plop into bed and fall asleep. That would be a steady state. Okay? Everything in nature wants a steady state. But you're alive. So while you are living, fill your brain with information, fill your body with good food and exercise, explore your surroundings while you have the opportunity. After you die, you have all of the time in the world to be stable. So until then, a little bit of instability is okay. All right, so moving right along before you folks are too concerned about me. But let's look at this diagram. Let me go back first. Notice in this diagram here, we've got two atoms. One atom has how many valence electrons? That's right, one. And the other atom has how many valence electrons? 7. Now, in chemistry, 8 is a magic number. 8 is a magic number in certain respects, okay? Because in the second and the third energy levels, there's a seating capacity of 8. But the real gist of it is that the seating capacity is 8. If you can achieve that maximum seating capacity, then you, as an atom, are going to be happy, content, or stable. So let's look at this again. Look at this atom on the right-hand side. It has 7 valence electrons right now. Now, we can assume that this is either the second or the third energy level for the time being. And how many electrons would that atom like to have? It would like to have 8 maximum seating capacity. So how many is it short? How many is it missing? It has 7, wants 8. How many more does it need? Yeah, it needs 1 more, right? Now, let's assume this atom on the left, let's assume this is the third energy level that's being illustrated here. How many valence electrons does it have? That's right, 1. Now, is it happy? Now, if it's the third energy level, how many electrons are in the second energy level, even though they're not represented here in this diagram? That's right, 8. Because remember, electrons fill up the stadium from closest to the nucleus further out. So in order for an atom to have 1 valence electron in its third energy level, its second energy level must already be filled with 8 electrons. Now again, look at this diagram and think for a moment. Both of these atoms, like everything else, want to seek a steady state. They would both be happiest, with a completed outer energy level. The atom on the right would be happiest to gain 1 more electron, and its outer energy level would be complete. This atom on the left would be happy to lose 1 electron because its second energy level has 8, and it would be complete. And they would both be happy if this element simply gave over its 1 valence electron. And so in an ionic bond, that is exactly what happens. That is exactly what happens. Now, you have to think of it in terms of an energy point of view as well, and let me explain that. From an energy perspective, what do you think is easier? For this atom to lose one electron or this atom to lose 7 electrons? Or for this atom to gain 7 electrons? Lower the number, the less energy. And atoms, just like you and me, are also lazy. Remember inertia? So we all try to find the easiest way of doing things from an energy perspective. It's going to be a lot easier to lose one electron than to gain 7 of them. And so that's what happens from an energy point of view. But this is getting deep, it's getting complicated. Remember talking about neutral atoms having a balanced number of positives and negatives? Oh boy, what happens here? If this element on the left is losing a negative, it becomes a positive ion because there's now going to be more positives than negatives. And the atom on the right-hand side, it's gaining 1 electron. It's going to now have more negatives than positives. It becomes a negatively charged ion. See how all of these words are tying together, which is why it's so important for you to be studying your vocabulary every day. So, wow, we just said a mouthful with this diagram and what's happening here, but there's some good news at the end of this ionic bond because now we have a positive ion and a negative ion. They are both now stable with that movement of the electron. And now, since they are oppositely charged ions, there's an old statement in love: opposites attract. That's right, you heard it. This is the chemistry of love. Ionic bonds. Atoms are attracted to one another because of opposite charges. When atoms form ions of opposite charges, opposites attract one another. And that is the bond that holds ionically bound compounds together. The movement or the transfer of an electron forming ions of opposite charges, and opposites attract. Let me give you a real life example here. In this example of an ionic bond, we've got 2 elements. We've got Na, which is the symbol for sodium, and we've got Cl, which symbolizes chlorine. Now, let's attach names to these atoms, and perhaps it will make more sense, okay? Let's call this, instead of sodium, let's call it Nate. Here we have Nate. And Nate looks over and sees Clarice. And Nate looks at Clarice and says, "Ooh la la, Clarice looks pretty cute to me." And Nate and Clarice are far away from one another on the periodic table, but they do have some common needs, if you know what I mean. Nate needs Clarice, and Clarice needs Nate. And so eventually time passes, and as they get closer to one another, Nate can't wait. Nate can't wait any longer. So Nate gives Clarice a wedding ring. And they get married together to form a couple or a compound of sodium chloride, Nate and Clarice together at last, because this is what is happening atomically. Sodium starts off a neutral atom, 11 protons, 11 electrons, same number of positives and negatives. Here's sodium. Chlorine, look at the periodic table if you don't believe me, starts off as a neutral atom with 17 protons, 17 electrons, same number of each, neutral atom, chlorine. But neither one of them is stable because their outer energy levels are not complete. So what happens when they get close together? Fireworks. Remember watching the alkali metals react last week with those videos? Oh, yeah. Alkali metals like sodium, when they see their true love, fireworks erupt. That's right. And they want to get married right away. And so that's what Nate does. Gives his only valence electron over to Clarice, which changes the balanced number of electrons and protons with each atom, but they both become stable. They're no longer lunatics. Sodium is no longer this deadly, dangerous soft metal that is highly reactive. Chlorine is no longer this dangerous, poisonous gas because when they both come together in the form of sodium chloride, it is a stable compound which we can't live without. We need sodium chloride in our bodies, or our brains and our bodies wouldn't be able to function. And the thing that holds them together is the fact that they form ions of opposite charges. And as the saying goes, opposites attract. So that's the basic gist of ionic bonds. I hope you got that. If not, feel free to watch that segment over again. But now let's move on to the second type of bonds called covalent bonds. Covalent bonds. Look at the prefix, by the way, co. And look at the suffix, or the main root word there, valent. If you look at valent, I'm sure you can imagine what valent refers to. Our favorite word this week is valence electrons. Yeah. But the co, what does co mean? Think of other words that begin with the prefix co, like co-worker, cooperate, coefficient, co-mingle. I don't know. You can think of lots of co-words, right? Well, in this context, the word co means kind of cooperate or working together. So when you think of covalent, think of cooperate, working together, because covalent bonds involve a sharing of valence electrons. They are shared between two atoms, and that sharing is what holds them together. So it's not a fireworks kind of relationship that we had with ionic bonds. Covalent bonds tend to be, well, a little bit more subtle. Now, which one is stronger? Well, that might be up to you to decide in the laboratory. But for the time being, here's a visual image I like to think of with a covalent bond. I like to think of either kindergartners or elderly couples. Have you ever seen kindergartners or preschoolers walking down the hallway using the buddy system, holding one another's hand as they go deliver a message to the office? They are cooperating with one another. Or have you ever seen an elderly couple walking hand in hand, basically holding each other up from falling? They are both cooperating. And I think both pictures are beautiful pictures of cooperation. And in my mind, it illustrates what's happening with covalent bonds. Covalent bonds. Imagine we've got these two atoms, one on the left, one on the right. And both of them only have, and let's assume for a moment is the first energy level with both, and they both only have one valence electron. If we separate these two atoms, this atom would have only one valence electron, this one would only have one valence electron, and they'd both be unhappy. They'd both be unstable. But when they get close enough together, each of them share their electrons, which then orbit both of the nuclei together. And it is that sharing of the valence electrons which bonds these covalently bonded compounds together. Let me give you an illustration here, real quick, of a covalent bond. Think of hydrogen. Hydrogen here, number one on the periodic table. Number one because it has only one valence electron. Two hydrogens floating around by themselves are lonely things. But when hydrogen comes near another hydrogen, they both intuitively say, hey, two is better than one. Why should we be alone when we can share our valence electrons? And that is exactly what they do in this case. You very rarely ever find hydrogen as an atom by itself because it's so unhappy. In nature, you'll always find hydrogen buddying up with another hydrogen. It is the true buddy system here that illustrates covalent bonds. Covalent bonds, they share their valence electrons. And so that brings us to the third and final type of bond, metallic bonds. Metallic bonds, as the name certainly implies, involves atomic bonds associated with metals. And with metals, with a metallic bond, we don't have a transfer of electrons as we have in ionic bonds. We don't have a sharing of electrons as we have in a covalent bond. We have a sea of electrons. What do I mean by that? Well, when I think of metallic bonds, I think of Metallica. Have you ever heard of Metallica? Anybody know what Metallica is? It's a heavy metal band. Now, I've never been to a heavy metal concert, but I've seen them on TV. And I can only imagine that at a heavy metal concert, like at a Metallica concert, there might be body surfing going on in a mosh pit, perhaps. I don't know. I've never been there, but I've been told about this body surfing. Well, what is body surfing? Well, if you don't know what body surfing is, I'll tell you. It's when people jump up on top of a crowd and are lifted up by others, and their bodies are moved from one group of people to another, basically surfing on top of the crowd. I think that's actually a very good illustration of what happens to electrons in a metallic bond. Metallic bonds involve this sea of electrons, which happen to be the valence electrons that are free to swim or move back and forth from one atom to another, kind of like body surfing at a Metallica concert. Now, this idea of valence electrons being free to swim back and forth between different metallic atoms enables metals to be excellent conductors of both heat and electricity. After all, think about what electricity is. Electricity is the flow of electrons. So if something is held together with a metallic bond, as metals are, you've got a free flow of valence electrons. That's what electricity is. It's kind of cool when you think about it. Okay? So metallic bonds aid in a metal's ability to be an excellent conductor of heat and electricity. Okay, let's illustrate this with a diagram here. And we're going to finish up with this diagram for today. So imagine this is a hunk of metal or something held together with metallic bonds. We've got the positively charged nuclei of atoms because the protons in the nuclei. And we've got the valence electrons, which are free to swim back and forth between the various atoms. That is what enables metals to be good conductors of heat. By the way, that's supposed to be a flame there. Heat is energy flowing through the metal, and electricity, which is nothing more than electrons flowing through a metal or another substance. But metallic bonds, great conductors of heat and electricity because of the free flowing nature of the electrons, the valence electrons. I hope you've been able to see today how vitally important the valence electrons are in any one of these three types of atomic bonds that can take place between substances. Valence electrons are essential, and stability is essential in achieving the ultimate goal of stability. And it's what determines whether or not certain elements on the periodic table are going to react with other elements on the periodic table. And that's what our next few topics are going to be all about, the chemistry of reactivity of different elements. So stay tuned for the next couple of topics where we really explore some fun. But until then, I want you to really grasp the meaning of what is happening to valence electrons and why when different types of bonds are achieved. So feel free to refresh your learning of this topic by watching this video again. Otherwise, we'll get ready for tomorrow's lab activity. And until then, I'll say bye-bye.